What is a transaction, and why is that necessary for some applications? How do we define a transaction? Can transactions run concurrently, or does each one of them has to run on its own? And what are the risks and benefits of each? What are the asset properties, and how do they relate to transactions? All very important questions, so let's dive in to see the answers. Hello and welcome. My name is Elhelw. Today we are going to be talking about transaction processing. We're going to define what a transaction is, why is it needed, and we're going to talk about some of the problems associated with transaction processing, especially when they are working concurrently. Lastly, we're going to talk about some of the characteristics of transaction processing systems. All right, so let's start by talking about a transaction processing system. What is that? Transaction processing system is a system that has usually a large database and has many users and many operations that are running on it, usually concurrently. It requires, high availability and fast response times. There are multiple transaction systems that we deal with, in our everyday life, things like, banks, credit cards, payment systems, online reservations, e-commerce, things like Amazon, whatever you're buying stuff online. These are all transaction processing systems. Many people will be using the system at the same time. Each person will be doing their own transaction on it. For example, if we're talking about banking, someone might be withdrawing money, someone might be doing a transfer, someone might be depositing something, all at the same time in different areas. If we're talking about booking systems, for example, if you're talking about like a hotel booking system, many people would be searching for hotels. Some people would be looking at the same hotel, booking, rooms from that same hotel at the same time. Same thing that goes for online shopping. Many people will be browsing the same items, searching for items, looking at some of the prices, comparing items, and then putting things into the cart, checking them out, and so on. Some people might be actually like buying the same item at the same moment. So all of these systems, you can imagine, they have thousands of users at the same time, if not more. It must be available. It must be providing very fast response times. You cannot, click buy and then, wait for 20 minutes until it responds back to you. It has to be very, very fast. So those are examples of transaction processing system. What is a transaction? A transaction is an operation that you do on those systems, right? Usually, it's a logical operation that consists of multiple smaller pieces. So let's look at an example to see what that means. So let's take a payment, for example, if you're trying to pay for something using your debit card, right? So usually there are multiple steps that will be happening behind the scenes that all wrap within that concept of you making a payment. So those steps will look like this. The system will read your bank balance. It will check whether your balance is, sufficient to make that payment. So like if you're trying to pay this amount, the balance must be more than or equal to that amount. And then it will subtract the amount from your balance. It will pay that amount to the vendor, so transfer to the vendor's account, and then it will write the new balance back into your account after it has subtracted that amount from the balance. So all these steps together form the transaction of you making that payment. All of the steps need to happen in order for the transaction to be successful. Let's see how this transaction, how these steps work using an example. So suppose that you have $20 in your balance, in your bank account, right? And you want to make a payment of $50. So we're going to go over these steps one after the other and see what happens. So the first step is reading the balance. So it's going to get that amount from your bank account, which is 200. It's going to check whether the balance is greater than the 50 that you want to pay or not. Suppose that in this particular example it is, because you have 200. So it's going to subtract 50 from the balance. So now the new balance is 150. This new balance is only in memory, like we have not changed the amount in the database yet. It's going to pay 50 to the vendor, and then finally it's going to write the new balance. The new balance now is 150, so we're going to write that back to the database, overwriting the old one. So now the account has $150. So all these steps together form the transaction, from reading the original balance all the way to writing the new balance. Now, suppose that while executing these steps, some failure happens right before the final step. This failure could be something like network failure, disk failure, power outage, whatever it is. there could be, multiple different reasons for failure. So basically this means that we have executed all the instructions except for the one that writes the new balance back to your bank account. So this means that the balance has not been updated in the database. So now you still have 200 in the balance, but also the payment has been made somehow. There's money that got created out of thin air. Of course, nothing comes out of thin air. So basically what would happen if that's the case, then the bank would probably have to, figure this out. So this can, cause the bank a lot of problems, a lot of issues. So obviously a bank cannot allow a system to work in this way. So this is why we say that transactions need to happen, all of them, all the steps in the transactions need to happen, or we just cancel the whole thing and assume that nothing happened and we can retry it again at a later time. We're going to get more into details on that topic in a few minutes, so just bear with me. Just wanted to give an example of what a transaction may look like. So let's try to come up with a formal definition of a transaction from a database point of view, right? So out of the database, a transaction is just a sequence of operations. When we saw the example, we had some I/O operations like reads and writes, and we also had some other, processing operations like, some, subtraction or addition or whatever arithmetic that's happening during the processing part of the transaction. From a database point of view, the database only cares about the reads and the writes. It cares only about the data that it has. When is that data being read? By which transaction, and when is it getting written, updated, and so on. So from a database point of view, a transaction is a sequence of read and write operations on database objects. When I say database objects, I don't necessarily mean, object-oriented databases. I'm just talking about any database item that we can read and write. This could be a full table. Table is a database object. A row is a database object. A column is a database object. So all of these are database objects. So you can think of it just in more abstract terms instead of thinking about rows. But if you want to think of objects as rows, if that will make it easier to understand, then by all means feel free to kind of conceptualize it that way. So in SQL provides ways to actually define transactions. If you don't define transactions, then each query is its own transaction. Each query, each update statement, each insert statement, these are all their own transactions, unless you want to define a bigger block that contains multiple operations. So to do that, different database management systems have maybe slightly different syntax, but most of them would have a begin statement in the very beginning to say, okay, this is the beginning of a transaction. Everything that comes after the beginning belongs to that transaction until you reach either a commit or a rollback statement. Commit means that basically everything that's happened, all the changes that have been happening before, persist those changes and assume that this transaction is successful. Rollback means basically roll back or revert all the changes, cancel this whole transaction. It's as if nothing happened before. Usually this is the structure of a transaction, but like I said, different systems have maybe slightly different syntax. So if we look at an example in MySQL, this is what it might look like. So you have a start transaction in the beginning, and then you have rollback and commit. Doesn't have to have both of them. You could have just one of them if you want. And you have, read and write operations as we see here. So read are basically just like SQL select statements. The writes are, in this particular case, we have update statements, but you could have also inserts or deletes. Anything that changes the data is considered a write statement. And you have other operations like, some if statements, some, assignment, stuff like that. So this is what a transaction would look like in MySQL, for example. If you look at Postgres, it may have some slightly different syntax. It still has, begin and end. It has, commit. Instead of a rollback, it's like using raising exceptions. But overall, again, very, very similar way of describing the transaction. So just wanted to give you an idea of what it might look like. It may also look slightly different if you look at, Oracle or SQL Server and so on. As I mentioned in the beginning, transaction processing systems, they usually allow concurrent transactions. Concurrent transactions meaning transactions that are running, in the same time, from different users or from different locations and so on. So if we look at the bank example, like I said, there might be multiple people, running transactions at the same time, withdrawing or transferring money and so on at the same time. If this is not handled carefully, it can cause some problems. What kind of problems? Let's look at the following example. Again, to our payment example, but suppose that there are two people, in this household, and they both have debit cards on the same account, right? And those two people are out shopping, buying stuff, and now they want to make their payments separately, and they happen to do that, around the same time. So the balance that we're starting with is 200. Now, one person wants to pay $50, and concurrently the other person wants to pay $30. So basically, each of them is going to hand over their cards or start paying, which will trigger this whole transaction separately for each of them. You can think of these transactions as something that's happening on two threads, for example. When you have two threads, basically the sequence of operation and the control can jump concurrently between these two threads. So you may have one instruction from the first thread and then jump to an instruction from the second thread and then go back to the first thread and so on. So this may happen here as well. So in this case, for example, first transaction is going to start reading. This is the read step. So it reads 200 from the database. We're going to switch to the second transaction. It's also going to read 200 from the database. Now it's going to start, running over the following steps, checking that the balance is greater than 50, subtracting 50 from the balance, paying 50 to the vendor. And the same thing on the other side, checking that it's greater than 30, subtracting 30, paying to the vendor. We get to the right step, so this one is going to write the value that it has, which is 150, and then the other one is going to write the value that it has, which is 170. So do you see the problem here? The problem is that we started with 200. We paid a total, or we were supposed to pay a total of $80, so we should have ended with 120, but we ended up with 170 still in the balance. So again, some money was created out of thin air because the updates kind of overrode each other. So this is one example of some of the issues that may happen once we have concurrent execution of transactions. How do we avoid such a thing? One might say, well, okay, let's avoid having things running in parallel. Even if we have multiple users trying to run transactions at the same time, just add them to a queue and start taking out of the queue one transaction at a time, finish that transaction, get the next one, and so on. This way we guarantee that the transactions are not interfering with each other. This is true. It will get rid of these problems, but it also makes the system throughput and response time extremely bad. The resource utilization is also extremely bad. Why? Because when you're working just on a single transaction at a time, this transaction, as you have seen, it has some I/O, it has some CPU costs, right? Like at some point it becomes CPU heavy, making all these calculations and checks and so on. While it's doing that, the disk is idle. And while it's doing I/O, the CPU is idle. So the resource utilization is not great. And also because you have all these transactions happening one after the other, the response time ends up being bad. So because the user who issued the 10th transaction now has to wait until all the previous transactions are done, and they're just waiting, they're not knowing what's going on until eventually it's their turn. So this is obviously not a great way to do it. So we need to allow the systems to execute or run transactions concurrently, but we need to figure out how to do that while making them act correctly on the data. So to do that, database researchers came up with this concept of some properties or some characteristics to define that can basically define the behavior of different systems. So each system can say that I provide the certain guarantees regarding these characteristics, and then you can decide based on your application whether the guarantees provided by the system on these characteristics are suitable for your application or not. So let's talk about these characteristics and see what they mean and how they affect transaction processing. You may have heard this term before, ACID properties. So ACID is an acronym of 4 letters that express these characteristics that we have just mentioned. A is for atomicity, C is for consistency, I is isolation, and D is durability. These are the 4 properties that we're talking about. We're going to talk about each of them in detail, but just let me go through them quickly. Atomicity means that each transaction is all or nothing. Consistency has to do with the state of the database before and after a transaction. We'll talk about that. Isolation, meaning that ideally transactions should act as if each of them was executing in isolation with no interference from other transactions. This is not always possible, and we'll talk about that as well. And then durability has to do with the data that has been committed to the database and the fact that this data should be durable even if a failure happens later on. So let's start talking about these one at a time. So starting with atomicity. Atomicity is something that we've talked about in the very beginning. Something atomic means that you either take all of it or you take none of it. You cannot pick and choose which instructions or which operations in a transaction you want to execute, or if a failure happens, you cannot say, okay, like the first two operations have been successful and I will stop there. You either take the whole thing or you cancel the whole thing. We've seen that in the first example, but let's go through that again. So suppose that we have a transaction that looks like this. It has some reads and writes and some processing in the middle as well. And we have the begin and the commit statements. So let's say that before running the transaction, you have A equals 500 and B equals 200. Those are some database objects or values in the database. Now, what's going to happen once we start with this transaction? So first thing, we're going to read the value of A, which is 500. Internally, it's going to subtract 100 from A. So now internally, A is 400 in the memory. And then we're going to write that 400 back to the database. I wrote it in this yellow with the dotted line after it or around it because even though it's written, it hasn't been committed yet. So think of it as somewhat, of a intermediate, state of the data. Even though we have written it to the database, it's not committed. Now we're reading B. B is 200. Add 100 to that, so that's 300. And that we write the 300 to the database, also in uncommitted state. And then we reach the commit operation. So now these two are persisted in the database and the transaction is done. So before we had 500 and 200, after we had 400 and 300. So basically this is like an account transfer transaction. We transferred $100 from account A to account B. Now, let's go over that same scenario again, but with a twist. So starting from the beginning, again from 500 and 200, reading A, subtracting 100, writing A, so now it's 400 uncommitted, read B 200, and then some failure happens, right? Like I said, this could be disk failure, network failure, power outage, earthquake, whatever it is. Something happened and we could not continue that transaction. So if we stop right we are and we say that, okay, like this is the data that we have, this is not correct because we subtracted 100 from A, but we did not add that 100 to B. So basically $100 just disappeared in thin air. So this is not atomic if we stop this way. We either continue the whole transaction, or if something like this happens, we need to roll back and cancel any operation that we did, and we should go back to the initial state saying that A equals to 500 so that we can retry that transaction later on. This is what we mean with atomicity. So atomicity for transactions means that you either execute and commit, or you roll back the whole thing. The second property is consistency. Consistency has to do with the state of the database. The state of the database meaning that you assume that the data in the database is consistent, which means it's correct. Consistency is usually defined by constraints that you create on your database. Things like primary keys, foreign keys, null constraints, saying that a column could be null or cannot be null. Things like check constraints, saying that columns A plus B have to always add up to 100, for example, or something like that. So you could have many of these constraints, and the data is said to be consistent as long as all these constraints are satisfied. So a transaction, obviously, it operates on the data that is already in a consistent state, and a transaction is supposed to take the data to a different state that is also consistent. So you may do whatever operations on the data. You can subtract, you can delete, you can update, you can insert new data, whatever. But the final state of the database has to also end up in a consistent state. So this is what it means when we talk about consistency. Consistency is usually something that is easy to do once you're dealing with single server, right? Once you start having scalable databases and replicated databases, this becomes a little more tricky because you may do an operation, for example, that writes data. Usually you write data to one of the nodes or one of the servers that you have, and then this data gets propagated to other nodes when you're doing replication and stuff like that. So the server where you wrote the data, for example, is consistent, but the others have not been consistent yet. So let's say if you do a query after that and you start reading and your query gets routed to a different server before the data has been propagated, then you might read different information. So there might be some issues with the consistency. The more scalable your database is, the more you can see this problem. One example of that, if you think about, for example, social media, right? You could, let's say, put a comment on someone's post, right? And if you refresh the page right away, you may not see that comment. But if you refresh it again, like let's say in 2 or 3 minutes, the comment will be there. So in that intermediate window, the data was not consistent. But eventually it became consistent. This is something that they sometimes refer to as eventual consistency. Some systems, especially like systems that are highly scalable, they do not provide like instantaneous consistency. They sometimes provide like eventual consistency guarantees. So if you hear that term, this is what it means. That even though the data may not be consistent, like, at any given moment, eventually it will be consistent. All right, jumping on to the next property, which is isolation. Isolation is one of the most important parts probably when you're talking about concurrency control. The idea, or in an ideal world, even though transactions, we establish that we don't want to run like, one transaction at a time. We establish that we want them to run concurrently with, instructions interleaving and so on. But in an ideal world, even though that's happening, we want them to act as if each one of them has been running in isolation. So basically, we want the illusion of no interference between these transactions in an ideal world. But this is not always possible. And also, it's not always required. Like some systems may be a little lenient and they don't really require that kind of like, strict requirement. They may be okay with some data changes that might not be super accurate. So there's always a trade-off between how much accuracy you want in the results and how much throughput and concurrency you want to allow. Let's look at an example and see the base case of transactions that are acting in isolation. So let's say you have these two transactions, T1 and T2. You have the timeline on the left side. So in this particular case, basically T1 is acting or executing alone, and then once it's done, T2 will start executing. So say that we start with A equals 500 and B equals 200. Let's go through the steps and see what's the end value here. So A will be read in T1, that's 500, subtract 100 and then write the result. So now we're going to write 400 in A. Again, this is not committed yet. I also did not write the commit statement here, but assume that the end of the box is the commit statement. Then we're reading B, which is 200, add 100 to that, and then write the new value. So it's going to write 300 to B. Now T1 is going to commit. So these two values are going to be now committed values. T2 is going to start. It's going to read A, which is 400, add 50 to that, and then write the new value, 450. Now, and then they commit. So now the final results are A equals 450, B equals 300. So this is the output if each of these transactions was executing completely in isolation. Now, like we said, this we call this serial execution because they're just like executing in sequence one after the other. Serial execution doesn't have the best throughput, obviously. So we want to try to interleave those transactions, allow them to execute in an interleaved concurrent fashion, and see what the output would look like. Of course, there are many different ways in which these transactions could be interleaved, depending on which, like the timing between the different operations on both sides might be different. So some of those scenarios may end up giving us correct results. Some of those scenarios may end up giving us different results. So let's see an example. So say that the transactions now are starting at the same time and the individual operations are going to be interleaved in this way. Again, starting with these values, let's see what happens. So the first instruction is reading A. So A equals to 500. Subtract from A and write the new value. So now we're writing 400. Again, not committed yet. But now we're going to jump to T2. T2 is going to read A, which is 400. We're jumping back to T1. So T1 is going to read B. That's 200. T2 is going to add 50 to A, while T1 is going to add 100 to B. And then T2 is going to write the new value. So 400 plus 50, that's 450. So it's writing that to A. And T1 is going to write the new B value, which is 300. And then both are committed. So this is the final value. This is the same value that we got when they were acting in isolation. So Even though we have interleaved the transactions, we still got the same value. In a different interleaving, so it could look this way. Let's see what happens here. So A is equals to 500. We're going to subtract 100 from that. And then T2 is going to read A as well, which is still 500. It's going to add 550 to that. Now T1 is going to write A, so 500 minus 100, that's 400. So it wrote 400 into A. It's going to read B, which is 200. Now T2 is going to write A. The value that it read was 500, and it added 50 to that, so it's going to write 550. Then jumping back to T1, adding 100 to B and writing that, so B is 300. Now when these two are committed, B is correct, but A is not. The correct value for A was 450. Now I have 550. This happened because the update from T2 overrode the update from T1. So it's basically like T1 did not change A at all. If we started with A equals 500 and we did only T2, this is what happened. The update of adding or of subtracting 100 was overwritten. So this is one of the problems that happens when we interleave transactions. This particular problem is called the lost update for obvious reasons. One of the updates was lost. So there are multiple other problems that may happen due to this concurrent execution. So let's go over some of the common problems. We already talked about the lost update, which was just seen. There are two other very common problems. One is called dirty read, and one is called non-repeatable read. There might be others as well, but let's just talk about these two. So dirty read, what does that mean? Dirty read meaning reading a value that has not been committed yet, or a changed value that has not been committed yet. We've already seen that actually in some of the examples, but let's go through that again. In some cases, this might cause issues, but in some cases it might not. So depending on the situation, it's not always bad by default. Some cases might be bad, some cases might be okay. Let's look at this example. Again, starting with these values. So reading A, that's 500. Subtract 100 and write it back. Now we have 400. T2 is going to read A, so it's going to read that 400. This is the dirty read. So because it read a value that has not been committed yet. Let's continue. Read B, that's 200. And then T2 is going to add 50. T1 is going to add 100 to A and B respectively. And then T2 is going to write the new A value, which is 450. T1 is going to write the B value, which is 300. And both are committing. And in this case, we ended up with the actual correct numbers. So even though we did a dirty read here, it did not cause a problem in this particular scenario. Let's redo this example again, but we're going to have a different conclusion. The same exact interleaving of operations, right? Starting with these values, again, reading A, writing the new value, which is 400. T2 is going to read that 400. Again, that's the dirty read that we have. And then going back to T1, a failure happened and we had to roll back the T1 transaction. Rolling back T1 means that every change that has been done by T1 has to be canceled. So updating A from 500 to 400, we need to cancel that and we need to go back to A equals 500. So we did that, rolled back T1 completely. However, T2 is still going. T2 did not fail, so T2 should be able to continue. So it's going to add 50 to the value of A and then write that new value. However, the value of A that it read was the 400, so it's going to put A equals 450 because it added 50 to that 400 that it read, and then it read that new value and committed. Now we have A equals 450. Because we rolled back T1, right, then this means that the only transaction that actually succeeded was T2. T2 adds 50 to A. If we started with A equals 500, then you would expect to have 550. But because the value that we read was a dirty value, and we built on top of that, and then the transaction that wrote that value actually ended up rolling back, then we ended up with the wrong solution. So this is a problem that might happen because of the dirty read. Let's look at the other problem that we mentioned was the non-repeatable read. Suppose that we have these two transactions. T1 reads from A, has multiple reads from A for whatever reason, and then some other processing in between those reads. And T2 adds 50 to the value of A. So starting with A equals 500, T1 reads 500, T2 reads 500, adds 50, and then writes the result. and then T2 actually commits. So T2 is completely done. This value is committed. Now T1 wants to read A again. So now it's reading 550. So this is not a dirty read, right? Because it read a committed value. So we don't have a dirty read problem here. However, T1, from a T1 perspective, it read A multiple times, and each time it got a different value. So we call this a non-repeatable read. This may or may not be a problem, again, depending on your application and depending what you're doing with the data. So to address all these problems, database systems started defining something called isolation levels. Isolation levels, you can think of it as a spectrum that addresses the trade-off between isolation, meaning trying to have transactions operate completely separate from each other with no interference, and the other end of the spectrum is everything is interleaved, because isolation comes with reduced throughput and reduced response time. Concurrency comes with better throughput and better response time. So there is a spectrum between these two, and this is where the isolation levels come in. So each database may support one of these isolation systems, and depending on that, you know which problems you may run into. So the first isolation level is called read uncommitted. Read uncommitted means that each transaction can read whatever. It can read any data, whether it's committed or not, it doesn't care. So basically this is the most relaxed level. It has no isolation at all. It has the most concurrency, best throughput, but no guarantees on the correctness of the data, because each transaction can read whatever. You could get into all sorts of different scenarios. This might be acceptable for your application, in which case it provides really good performance. The next level is slightly more restricted. It's called read committed. So basically means that each operation within the transaction can only read data that is committed. Any uncommitted data, it will not be visible. Only the committed data will be visible to any reads. So basically this avoids the dirty read problem. If you have any dirty data and you have a read instruction, it will not see that new dirty read until it gets committed. It will read, the previously committed value. However, if you have multiple reads within the same transaction, like we had in the non-repeatable read, right? Like the value was committed, so it would see it. This gets rid of dirty reads, but it does not get rid of the non-repeatable reads. The next level is called repeatable reads. Clearly, it addresses that problem. So this means that basically at the beginning of the transaction, anything inside this transaction will only read things that were committed at that beginning. So any new commits will not be visible to that transaction. So this means that if you read the same value multiple times, you will always get the value that was visible when the transaction started. So you will always get the same value. So this handles the non-repeatable read problem. And then the final level, which is called serializable, this is like the most safe. It basically means that transactions act as if they were all, running in isolation, that there's no concurrency. This is the most restrictive level. This, addresses all the problems that exist out there. This is needed if you really require, these high guarantees of isolation and of data accuracy. So depending on your system, you could choose one of these levels. Also, different databases may say that they provide, certain isolation levels. So that is something that you also can look out for. The final property is the durability. Like we said, durability means that any changes that have been committed have to be durable, have to be persistent in the database. Even if a failure happens, like let's say you are withdrawing money from an ATM, for example. If the transaction returned to you saying that it has been successful, then even if a power failure happens later on, or if a disk failure happens later on, and then the machine restarts. When it restarts again, you need to see that the changes have already been persisted and they are still in effect in the database. They have not been canceled. So anything that has been committed is persisted. So there are many ways where many things that systems can do in order to ensure that this happens, like through recovery and so on. They can write logs with all the operations that they have, so that if a problem happens and then you have to do a recovery for the system, you can rerun all these instructions again to make sure that you reach the same point that you were at before that failure happens. Again, as long as these operations have been committed, or these instructions or these transactions have been committed. So this is what it means for a system to be durable. Of course, this only applies to disk-based databases. When you're talking about, let's say, an in-memory database, clearly durability may not apply there to the same extent because data is in memory. If anything happens, memory is volatile, so they may not provide these durability guarantees. All right, with that, let's summarize what we talked about today. Again, today we were talking about transactions and transaction processing systems. Transaction is a sequence of operations. From a database point of view, databases only care about the read and write operations. They don't care really about any other processing steps. This sequence of operations need to execute as a whole to consider the transaction successful. If there is any failure, you need to cancel or roll back the whole thing. We talked also about interleaved or concurrent execution, which provides better throughput, better response time, but it carries the risk of interference between these transactions, which may end up in unexpected results or unexpected changes to the data. This led to the definition of the ACID properties: atomicity, consistency, isolation, and durability. These are properties that define the behavior of database systems regarding these 4 axes. So atomicity means that you either commit the whole transaction, or for any reason to fail, you have to roll back the whole thing to guarantee that the data is in a consistent state. This is what we're talking about in terms of consistency. So a transaction needs to take the database from a consistent state to another consistent state. We also talked about eventual consistency and what that means. And then we got to isolation, and we talked about the trade-offs between having the transactions run in isolation, which provides the better guarantees in terms of the data and the changes and so on, and the other extreme of concurrent transactions and what potential problems could happen, like dirty reads, lost updates, non-repeatable reads, and so on. And then we talked about the isolation levels and how these isolation levels handle some of these problems. And lastly, we talked about durability and the fact that once a transaction is committed, its changes need to be persistent in the database, even if a failure is to happen after that. I hope this was useful, and I hope it was clear what we were talking about today. If there are any questions or anything that's not clear, please leave it in the comments and I will try to get to it. Otherwise, please like the video. Please subscribe to the channel if you have not subscribed already. And with that, thank you so much for watching, and I will see you in the next video.